In your science packet, you should find page 6. Page 6 says Topographic Map A. This is a topographic mountain of a mountain that is found in the Cascade Range. Let's observe the different contour lines. If we start at the outer contour line, we notice that its elevation is 1,500 feet. More we go up, we notice that the elevation increases to 2,000 and 2,500. Now I have a picture of another map. If you have your science packet, please turn to page 8. Page 8 shows us a copy of Topographic Map B. Let's take a look at the elevations on Topographic Map B. When we look at the elevation of Topographic Map B, it has an elevation that starts at 1,500, increases to 2,000. However, the next elevation point on the contour line is also 2,000. Now, we are not sure what mountains these two maps show, but let's compare a side-by-side Topographic Mount A and Topographic Map B. Do you think these are the same mountain? Take a closer look. I noticed that these mountains have different elevation points. For example, Topographic Map A, it has a high elevation point of 2,500 feet. However, Mountain B, Map B, its elevation point is of 2,000. However, if I look at the shape of the mountain, it follows a very similar outline. For example, I noticed that on side A, this outer line follows a very similar shape that I can also see on side A of mountain B. Or if we look at the contour line of 2,000 on mountain A, has a lot of bumps, has a big bump over here. And then if I look at mountain B on that same contour line, it follows the same shape. The difference I notice is the contour lines on the north side, which are over here. This is where the shape begins to change, and Topographic Map B has a much bigger shape, versus over here it still follows those lines. Well, I would like to share with you that both Topographic Map A and Topographic Map B both show a topographic sample of Mount St. Helens. Mount St. Helens is part of the Cascade Range in California, close to Mount Shasta. On May 18, 1980, Mount St. Helens erupted. When Mount St. Helens erupted in 1980, it gave scientists and engineers a chance to learn more about how volcanoes formed. This is what, after its eruption, when scientists were able to create a new topographic map, this is what Mount St. Helens looked like. Do you think the mountain range got taller or smaller? This is the topographic map of Mount St. Helens before its eruption in 1980. Before the mountain erupted in 1980, the last time it had erupted was in 1857. It had been quiet for more than 120 years. Generations of people have lived near the mountain, enjoying its view and never imagining that it would erupt again. They probably thought it was an extinct volcano. However, when it erupted in 1980, they did not expect what it was coming. We are going to create a profile so we can get a look of what Mount St. Helens looked like prior to its eruption, and then we are going to compare it to what it looked like after it erupted. If you have your science packet, please go to page 7. On page 7 is where we will create our profile. We need to write a title. Our title is Mount St. Helens. And we are now going to add the different elevation points. To figure out where to start our elevations, we need to look at our topographic map. Our lowest elevation is 1,500 and our highest elevation is 2,500. In order for all our elevation to fit on our map, let's start by 1,200 and then count up and then increase each line by 200. So our first one is going to be 1,200. Our next line up is going to be 1,400. Our next one up is going to be 1,600. $1,800. Notice for how my elevation, I'm just adding 200. So 1,800. We're gonna go next to 2,000, 2,200, 2,400, 2,600, and we're going to go to 2,800. Let's begin using our topographic map to draw a profile of Mount St. Helens before its eruption in 1980. So the first thing we want to do is fold it down this line so that we are able to line it up. Alright, so you want to have folded the topographic map so you can see the letter A and the letter B. And now we're going to start at the bottom. Now my friends, when we look at our topographic map, we notice that it starts at 1,500, then it skips some lines in between and goes to 2,000. It skips some more, then to 2,500. However, only because it is not written on the map doesn't mean that those contour lines aren't real or that there's no elevation. When we count in between the 1,500, it is going, the contour, the elevation is increasing. Let's see, it is increasing by 100. Watch. 1,500, 1,600, 1,700, 1,800, 1,900, and 2,000. So our contour interval is of 100. If we're following our contour interval of 100 and we're at our 2,000 line, and then we go up to the next line, what is our elevation if here? If you said 2,100, that is correct. Our contour interval is 100 feet. So if we're here and we go up another elevation, it's 2,200. Then it goes up to 2,300, 2,400, and 2,500. Even till we get to the top, 2,600, 2,700, 2,800, and at the very top we have our peak, which is at 2,900 feet. Alright, so with that information, let's begin building our profile map. There is no elevation of 1,400. Let's keep moving up. But there is an elevation of 1,600. And if our contour line tells us that if this is 1,500 and we're increasing by 100, the elevation of 1,600 is this line. So let's trace this line with our finger all the way. We're going to draw our first dot right there with where our contour line meets 1,600. Alright, let's move up to our elevation of 1,800. This was 1,600. This line was 1,700. We're going to skip it and go to 1,800. We're going to trace that line. Sorry for that. We're going to trace this line of contour 1,800. And we're going to draw our second dot where, we're going to draw our second dot where our contour line meets our profile. Just right there. Now let's move it up to the 2,000 line. Our 2,000 contour line says it right there. It's that second bold line. Let's find it, trace it with your pencil, and we're gonna draw the dot right. And draw the dot right there. Alright, let's move up an elevation of 2,200. Our elevation is 2,000. We go up 100 feet. That is 2,100. Let's go up another 100 feet. That is 2,200. So this second line, we're tracing it. And we find that it is right here. Our next elevation point is 2,400. We had this line, which was 2,200. We go up 100 feet, 2,300. Go up another feet. This is 2,400. We're going to put our dot there on where the 2,400 contour line meets with our profile. We're gonna go up to our next elevation, which is 2,600. We see on our map that the next bold line says 2,500. We're gonna go up 100 feet to the 2,600 line. We're gonna draw a dot there. Good. Let's move up to 2,800. This is 2,600, 2,700, 2,800 is this one right here. And our next contour line goes up by another 100 feet. So that's 2,900, which means we're not all the way at the top to the next line, but we are going to draw a line so we know where our peak is at. So at this point, we have gone up our map, up our mountain. We just have to come back down. We're gonna we drew our peak. Let's work our way down to the 2,800 line. So now we're counting down, which was this line here. And we know that this line is the 2,800 interval contour line because this is 2,500 and each contour line goes up by 100. So let's add our dot there. Let's move down to a lower elevation of 2,600. Our contour line of 2,600, it's that first line that is 100 feet above the bold line. So we're going to follow, instead of going to the right, you want to follow it towards the B side. See how there's a letter B here, and now we're going down the mountain and there's a letter B here. We want to go towards the right. So we found our 2,600 line. We're going to trace it going towards the letter B and draw our dot there. Let's move down to 2,400. We found the 2,500. We go down 100 feet to find 2,400. We trace that line towards the letter B and we draw its dot there. Working our way down towards 2,200. So let's count down. We were at 2,400. We go down 100 feet, 2,300, 2,200. So this line right here, we're going to trace to meet. Here. Draw our dots there. Right, we're going to move our topographic map down from 2,200. We're going to move it down to the 2,000 line. Our 2,000 profile. See how it says the 2,000 elevation on our map? We're going to find the 2,000 contour line. It says it right there. We're going to trace the 2,000 contour line towards the letter B. Find where it meets up with our profile and draw a dot. Good. Let's keep working our way down towards the 1,800. We were at 2,000. We go down 100 feet. That's 1,900. We go down another 100 feet. That's 1,800. We trace that line. We draw a dot there. Good. Let's keep working our way down to our next low elevation, which is 1,600, then 700, 1,600. Draw our dot there. Now we were able to make our map on our profile. We won't keep going down because our next contour line is 1,500. We're just going to stop at 1,600. So now, so we can finish creating our profile, we're going to start at the 1,600 line and work and connect the lines so we are able to see a clear picture of our profile. This is a profile of what Mount St. Helens looked like before its eruption in 1980. On March 20th of 1980, a 4.2 earthquake shook Mount St. Helens. Scientists took note about the earthquake, but didn't pay much mind to it until later. They started noticing some steam venting from Mount St. Helens. By the end of the month of April, the mountain began to bulge. They didn't expect Mount St. Helens to erupt. Matter of fact, they were using new equipment to that tracked how quickly a mountain bulges, and they thought the equipment was broken, because there is no way that Mount St. Helens, which has been dormant for more than 100 years, is bulging so quickly, to 5 to 6 feet a day. So it was bulging. It was getting ready to burst. Magma was building. It was bubbling up inside of the volcano, and it was bubbling very quickly. Finally, on May 18th of 1980, the bulging and the bubbling erupted. When the magma in Mount St. Helens exploded, it flattened everything in its path. Huge trees were knocked down in a matter of minutes, like if they were little toothpicks. Although it had a big impact, this was very important for scientists. It provided an opportunity to observe how volcanoes act when they are active. It was a learning opportunity. Scientists were able to learn how to prepare for volcano eruptions, or how to avoid different impacts it could have on people. Even something as simply as warning them, because when they saw that bulging, that was a sign that Mount St. Helens was bubbling up and getting ready to erupt. So this is what it looked like before its eruption. Following its eruption, scientists were able to build a new topographic map. Topographic map B shows us what the new volcano looked like. So we are now going to fold topographic B right down so we see letter A and letter B across, and we are now going to build the profile for topographic map B. So now we are going to build a profile for topographic map B. We are going to build our profile on the same map that we built Mount St. Helens. We're just going to follow side. We are doing this so that we are able to compare what Mount St. Helens looked like before it erupted in 1980 and what it's going to look like following its eruption. So we want to start out at the same point. We're going to start out at elevation 1,600. Our first bold contour line shows us that the elevation there is 1,500. We're going to go up 100 feet. We're going to draw our first point on our map following this elevation of 1,600. Let's move up to elevation 1,800. We're gonna go back to our map. We're gonna line up our map to elevation point 1,800. We're gonna find the 1,800 contour line. We were here at 1,600. We went up 100 feet, 1,700. We went up another 100 feet. This is the contour line 1,800. Let's trace this 1,800 line towards the letter A. The letter A is where we are going up the mountain. Let's move up our elevation to 2,000 feet. We're going to find our contour line of 2,000 feet. Follow our 2,000 contour line towards the letter A. Then mark it right where it meets. Most of our points while we are going up the mountain seem like they are in the exact same place. We are moving to the 2,200 contour line. To 2,200. Trace that line. Trace that line and draw another dot. Alright, let's move up our elevation to 2,400. There's 2,300. We move up to another 100 feet, and there is contour line of 2,400. So we're going to draw that dot on the 2,400 line. This is where it gets bit interesting. This is our 2,400 contour line. However, if we trace this line around, it seems like all of that is 2,400. Now you may notice these other lines in between. Those all are less. Next big elevation from 2,400, it's 2,000. But wait, if we're going up the mountain, up Mount St. Helens, and our last elevation was 2,400, why is our elevation going down? What happens to the top? If I follow this line, this 2,400 line, this line, it takes me there, but let's follow this line to see where it takes us. That brings me back to the 400. And then this line here, if I trace it around, this line is 2,200. So it looks like our elevation of our map has decreased. Our next one, the next line that we found was 2,200. Let's bring our map down. And we're going to trace it towards the side B. We're going to bring our map down to the 2,200 contour line. We're going to trace this line here towards the side B. Yes, I know it's a bit tricky to see. Is this line here, and draw a dot there. Down the mountain and find the 2000 contour line. When we trace it, it looks like it's right over here. Let's go down to the 1800, which was, this is the 2000 line. This 1900, 1800. We're gonna trace it. Looks like it's all over here. Bring it down to the 1600, which is this line. Notice how we were going up our mountain, and then once we reach the 2400, our topographic mountain didn't have a elevation anything higher of 2400. It started to go down to 2200, then 2000, 1800. On the 1800 line, let's move down 100 feet to 1700, another 100 feet to 1600, which is right around here. So now let's connect our dots to see what happened after its explosion in 1980. Some of the elevation points, for example, on the letter A, were at the same point before its elevation. So we're going to follow the same line. It was when we got to the 2400 that our mountain started to decrease to 2200, 2000, down to 1800, all the way to 600. So our Mount St. Helens, for its explosion in 1980, it was this tall volcano. Following its explosion, tall volcano lost a lot of feet. You think of volcanic eruption, it is usually for how it is part of the process of how mountains are built up. For example, a lot of the islands in Hawaii are built because of volcanic eruptions that have occurred, and magma has hardened and turned it into land. However, this volcanic eruption was different. The eruption of Mount St. Helens was so hard that Mount St. Helens blew its top off, literally. It reduced its height from being this high. It reduced its peak from being at 2,900 feet all the way down to 2,400 feet, losing about 1,300 feet in height. This whole entire side B, completely collapsed. Scientists and the people around there were not ready for that. And that's what caused a lot of mud to be flowing down, a lot of erosion and rocks breaking down. It caused a lot of damage to different trees and different homes and bridges that were there. So we can see its loss. Let's draw a dotted line. We're going to draw dotted lines going to signify that we're going down. We're going to draw those dotted lines so that we know how much smaller Mount St. Helens became. If we're to visit Mount St. Helens today, its peak is at 2,400 feet. It's not that high of a mountain. Tomorrow we will be looking at a video that explains its eruption and the changes that it caused and how it helped scientists and different people that study volcanoes.